Hello and welcome to today's webinar in partnership with Husky Technologies, hosted by Packaging Europe. In today's webinar, we'll explore efficient solutions for processing recycled PET materials by harnessing vacuum dryer technology. My name is Elisabeth Skoda. I'm the editor-at-large here at Packaging Europe. For those of you who are familiar with Packaging Europe, we are the leading intelligence resource for packaging professionals around the world, via our website, as well as online and in-person events such as the Sustainability Awards and Sustainable Packaging Summit. We deliver daily news content, authoritative comment and analysis, case studies, and high-profile interviews with leading industry players, and we enable communication across the packaging value chain. So a bit more about today's webinar. As both consumers and legislative demand for more sustainable packaging heightens, manufacturers need efficient solutions for processing recycled PET material. And today we'll discuss how upgrading aging desiccant dryers to next generation vacuum drying technology can transform operations. And you'll get real actionable strategies for advancing your rPET processing capabilities while boosting your productivity and profitability. And we'll discover how new vacuum dryer technology can help you enhance rPET material processing, enable application flexibility, gain significant energy efficiency, reduce maintenance costs, and increase processing customization. So with that, I'm very pleased to welcome our speaker today. I'd like to welcome John Murphy, who's Product Manager for PET Auxiliary Systems at Husky Technologies. So before I hand over to John, just a bit of housekeeping as well. There are 15 minutes at the end of this webinar reserved for a Q&A. And using the chat facility, please post your questions in the chat and I'll put them to a speaker at the end of this session. You can do this throughout the entire webinar and we'll try to get as many of your questions answered as possible. We also have a survey for you. Please make sure to fill that in before leaving the webinar today to share your thoughts about this webinar. You'll find the survey in the left-hand navigation under forms, and once this is live for you to fill in, you'll receive a notification on your screen. If you have any technical questions or issues, please select the support button, which you will see on the left-hand side of your screen. So with that, I'd like to hand over to John to get us started with your presentation. Thank you.
Thank you, Elizabeth. Hello, everyone. As Elizabeth just mentioned, my name is John Murphy, and I'm the Product Manager for PET Auxiliary Systems at Husky Technologies. I've been at Husky for a little over 10 years, starting as a mechanical engineer and holding roles in engineering, sales support, and now product management. The topic that I will be presenting to you today is something I'm very passionate about, and is a topic that Husky has built a very strong capability in. One of Husky's main pillars is sustainability. Husky has a deep experience in processing recycled materials, and this knowledge extends beyond just our injection molding machines. Today, I would like to talk specifically about the resin drying process. We'll begin with an overview of market direction before exploring the importance of the resin drying process. Next, we'll take a brief look at the leading technology in the field and dive deep into the challenges of processing rPET. I'll then introduce a groundbreaking technology designed to overcome these obstacles. To wrap up, I'll walk you through the technical details and highlight the value this technology is already starting to bring to the industry. When looking at the beverage, food, and personal care industries, we understand that there is a clear market direction towards more and more rPET usage. Manufacturers have sustainability goals, and consumers are increasingly demanding packaging that is lighter weight, contains more recycled material, and has a lower carbon footprint. Energy consumption not only supports sustainability goals, but also significantly influences production costs. As a key metric, it plays a crucial role in determining the most cost-effective way to manufacture products. We also recognize that there is a talent crisis globally. It is becoming harder and harder to find skilled labor. As we look to the future, Husky wants to continue to lead the way by having expertise and solutions to help customers achieve their goals. That means having systems designed to meet sustainability goals as more customers adopt circular economy practices. As well, the global talent crisis has resulted in a need for easy-to-use technology and equipment that is more automated and smarter, with an emphasis on maintainability. Large brands have been moving in this direction for some time, but the commitments are becoming more bold and more common. On this slide alone, you can see some sizable commitments from major brands spanning the food, beverage, and personal care industries. Some examples are PepsiCo with 40% by 2035, Nestle at 50% by 2050, and then as well, we see L'Oreal, for example, 100% by 2030. Now, before we go deep into resin drying technology, I would like to start with why drying is important in the injection molding process. Some common issues that you can see are bubbles that are caused in the preform. This occurs when there's too much water still trapped in the resin, which boils off during the melt process. This can lead to visual defects as well as poor blowing behavior. We can also see yellowing of the preforms, which is caused by degraded resin, which occurs by excessive drying temperature or for drying the resin too long. This leads to color deviation, potentially high levels of AA, as well as poor blowing behavior. We can also see haziness in the preforms, which is caused by using low temperature resin or having the moisture content too high. This leads to brittle bottles and as well poor blowing behavior. Lastly, we can also see IV drop, which is caused by too much water still trapped in the resin or due to thermal degradation at high drying temperatures or excessive exposure time. This as well leads to brittle bottles and poor blowing behavior. The result of these issues is increased scrap during the blowing process. Currently, the industry is dominated by desiccant technology. This technology is typically in the form of desiccant wheel or dual desiccant bed. For desiccant wheel technology, a wheel is rotated for continuous drying capability. The majority of the wheel is dedicated to process air being dried as it flows through the wheel. There is a small section of the wheel dedicated to regeneration heating and regeneration cooling. As the wheel rotates, the regeneration process is able to remove moisture from the wheel to make this a continuous process. For dual desiccant bed technology, the air flows through one tower containing desiccant material, while the other tower goes through a humidity-reducing regeneration process. As air flows through the desiccant tower, moisture is removed from the air and absorbed by molecular sieves. Once the tower has saturated with water, a valving mechanism switches to the other tower to create a continuous process. Both of these technologies have been in the industry for many, many years and are effective when drying virgin PET material. As the industry moves more and more towards processing of recycled material, we need to first be aware of the challenges this material presents. rPET resin is more sensitive to the drying temperature it is exposed to. Exposure at a high temperature for a long period of time can cause yellowing of the material, which is caused by thermal degradation. rPET material is also susceptible to condensable contaminant generation, predominantly when exposed above 160 degrees Celsius. Condensable contaminants can affect the performance and consistency of the desiccant dryer. Effective removal of condensable contaminants supports the highest preform quality. Recycled material often includes a higher quantity and variance of dust that is generated during transportation. Dust can generate black spots on the preform, so this can cause significant issues with your final part quality. The manufacturing process of rPET material can also lead to higher levels of acetaldehyde, or AA, leading to an off taste in the final product. Because rPET can come with varying levels of water content, it can be challenging to dry to a consistent humidity level. This inconsistent humidity level can lead to IB drop that affects the performance of the final product. And lastly, the manufacturing process can lead to lower crystallinity levels. This can cause issues with bridging or sticking in the hopper if exposed to high levels of heat. For more than 20 years, the beverage, food, and packaging industries have predominantly relied on virgin PET resin, with desiccant-based technology proving to be an excellent solution for processing this material. Over time, desiccant technology has continued to evolve, with steady improvements in performance. Even today, we see ongoing advancements, and Husky remains committed to enhancing this critical technology. However, we have now reached a pivotal moment, something I like to call the innovation window, where a breakthrough technology is emerging that offers a step change in performance, particularly when processing recycled PET. Vacuum technology has been specifically designed to meet the evolving customer needs highlighted earlier in this presentation. Over the next few slides, we'll take a deeper dive into this technology, exploring how it works and the tangible value it can deliver. Now, I would like to introduce vacuum technology. So unlike desiccant drying, which uses heated air and desiccant beads to absorb moisture, to absorb and remove moisture from resin, vacuum drying removes moisture by lowering the pressure, allowing water to evaporate at lower temperatures. As you can see in this chart, water has a boiling point of 100 degrees Celsius at atmospheric pressure. This is something that everyone is familiar with. What is interesting is that when you expose the water to a vacuum, you are able to lower the boiling point. You can see here on the graph that at minus 900 millibar, the boiling point is reduced to around 46 degrees Celsius. This reduced boiling point is the key to vacuum drying technology. Now that you've gained an understanding of the science behind vacuum drying, let's explore how this technology integrates into a complete drying system. Unlike desiccant dryers, which rely on a single large hopper, vacuum drying operates through 4 distinct phases, each serving a specific purpose. As you can see on the screen, and for those of you that are familiar with desiccant-based drying, this drying system looks quite a bit different. I'll start by explaining at a high level each of the 4 stages. So first, as resin enters the system, it begins in the preheating hopper in the top left of the screen, where it is heated to approximately 100 degrees Celsius to remove easy-to-remove surface moisture. Next, the material flows down into the heating hopper, where it undergoes further heating in preparation for vacuum exposure. From there, the material is transferred up to the top right of the screen, which is the vacuum hopper. In the vacuum hopper, the resin is subjected to vacuum conditions. This is effective in drying the material to below 40 ppm, making it ideal for the injection molding process. Finally, material is transferred to the post-heating hopper, where it is heated to the precise temperature required for the injection molding machine. Now that I've given you just a high-level overview, I do want to take the opportunity here to go a little bit more advanced and show you everything on the screen here. So this is showing the 4 stages which I just went through on the previous slide. Phase 1, the preheating hopper. Phase 2, heating. Phase 3, vacuum. And then phase 4, post-heating. On the right-hand side, you can see what's going on within each of these phases by showing the resin temperature and resin humidity. So we're heating up to 100 degrees Celsius, And if we consider an initial moisture content of 2000 ppm, we're able to get down to around 500 to 700 ppm in phase 1. In phase 2, we're heating up to 130 to 140 degrees, and we have no change in humidity level. In phase 2, it's a closed loop heating system just designed to increase temperature, not to remove any humidity. In phase 3, there is no change in temperature, but the material is exposed to that vacuum level, which is able to suck out the remaining moisture down to below 40 ppm. And then lastly, in phase 4, we have another closed loop heating system. So there's no change in humidity level, but we're able to increase the resin temperature up to 160 to 180 degrees, depending on what is best for your process. Now, what I'd like to do is go even deeper into the technology of both a desiccant-based dryer and a vacuum dryer, showing you exactly what's happening as the material flows from the top to the bottom of the drying process. So on this graph here, this is a desiccant-based dryer that I'm showing on the screen, and I'm tracking the temperature and moisture content as material flows from the top of the hopper to the bottom. So over the course of 6 hours, as shown on the screen here, we see that the material starting off at room temperature, or around 20 degrees Celsius, with a humidity level of approximately 2000 ppm of moisture. If we look at temperature first, the red line, we see a fast increase in temperature early on, where it slowly drops off in temperature as it approaches 180 degrees at the hopper outlet at the bottom. When we look at humidity level, we can see that we have a linear line to start off for the first hour and a half of the material being in the hopper. This is where we're able to remove that easy to remove moisture from the pellet at 100 degrees Celsius. However, after around 1.5 hours, we do reach a critical moisture level where now we have to remove that tough to remove moisture that's internal to the pellet. We can see a sharp drop off in the desiccant dryer's ability to remove this moisture. It takes the remaining 4.5 hours to get down to below 40 ppm of moisture. When we look at the vacuum drying system, we can see that there's a lot more going on the screen here, but I'm going to walk you through each of the phases so you can understand what's exactly happening within each phase. So we will start off on the top left-hand side of the screen, which is stage 1, the preheating hopper. We're starting off at the same conditions at room temperature, or 20 degrees Celsius, with a humidity level of 2000 ppm moisture within the pellets. In stage 1, we see a very similar situation as a desiccant-based dryer. We see the temperature increasing rapidly up to around 100 degrees Celsius, and we see a very stable linear line of moisture removal where we're able to remove that easy to remove outer moisture. At the end of stage 1, we do reach that critical moisture level where we have removed that outer moisture, but still have not removed the inner moisture. When we look down in the bottom left-hand corner in stage 2, there is no moisture removal. We see it steady, but we do see an increase in temperature where we're increasing from 100 degrees to 130, 140 degrees. From there, the material is transferred to the vacuum stage, or the top right-hand side of this graph. And here's where we really start to see a difference in the vacuum technology over a desiccant-based technology. Now we see an even more aggressive curve when it comes to moisture removal. From 500 ppm, we're able to quickly, over the course of an hour, hour and a half, reduce that moisture content down to 40 ppm. During this stage, there's a very, very small reduction in temperature just because of the evaporation of that water. And then when we look at stage 4, we see no change in humidity because we've already reduced to below 40 ppm, but we do see an increase in temperature up to around 180 degrees in this example, making it the ideal case for the injection molding machine. Before I move on from the technical section of the presentation, I do want to address a question that I often get about this technology. The question is, how are moisture and contaminants removed during the vacuum process? When material is under vacuum and the boiling point is reduced, water evaporates and is sucked into the liquid ring vacuum pump, which you can see in the bottom right-hand corner of the picture. Condensable contaminants are also evaporated and removed along with the water during this process. As dirty water and contaminants enter the vacuum pump, there is an automatic flushing process in place to ensure the pump is operating with clean water. Now that we've gone through desiccant and vacuum technology, I would like to go through a quick comparative of these two technologies. Desiccant technology is an excellent technology when processing a virgin PET resin. The drying mechanism uses dry air and moisture absorption. With respect to energy efficiency, it uses heated air circulation. And when we look at processing flexibility, we have one airflow and temperature setting with one large mono hopper. When we look at the maintenance of a system like this, there is maintenance required on a variety of different items, such as the desiccant towers themselves, the heat exchangers, as well as filters. To complete a resin change, it takes approximately 8 hours to remove the material and heat new material back up. And from a consistency perspective, it is a stable drying system, but we do see a slight variation when it comes to desiccant saturation and dew point temperature. Now, when we look at the vacuum drying system in comparison, the drying mechanism is quite different by using low pressure evaporation by changing the boiling point of water. When we look at energy efficiency and the processing of rPET material, there is no need for an oil condenser, which is a big advantage, reducing energy consumption significantly. With respect to the processing flexibility, because there are 4 distinct phases, there are multiple airflows and temperature settings, offering a little bit more flexibility. And when we look at maintenance costs, there are fewer maintenance items and lower upkeep, which I'll go through a little bit later in my presentation. Looking at resin change time, because there are 4 distinct phases, you are able to start loading a new material before you've finished drying your first material, reducing the resin changeover time down to 2 hours. And again, I'll go through this part a little more through my presentation. From a consistency perspective, we do see a relatively stable and controlled vacuum level as the means of reducing moisture. Now I would like to present the main topic of today's webinar, the 5 benefits that a vacuum drying system can provide when processing rPET material. The first benefit is energy efficiency. For processing virgin material, a desiccant drying system and a vacuum drying system are very similar in energy consumption, at around 70 watt-hours per kilogram in the best case scenario. Once we start looking at processing rPET material, we see a significant benefit in energy consumption for the vacuum dryer. A desiccant dryer typically requires an oil condenser that uses a substantial amount of chilled water to lower the temperature of the return air to condense out contaminants. Afterwards, the dryer must work harder to reheat that air before it is circulated back to the material. The chilled water requirement combined with the air reheat requirement results in an estimated additional energy consumption of around 30 watt-hours per kilogram, which is quite significant. On the other hand, the vacuum dryer does not require an oil condenser because contaminants are evaporated during the vacuum phase. This means there's no additional energy requirement when processing rPET material. The second benefit I'd like to show you today is lower maintenance requirements. On the left-hand side, you can see a typical desiccant-based drying system. We've recognized there are 4 main maintenance items that are required for a desiccant-based dryer. We have process filters, water heat exchangers, regeneration filters, as well as the molecular sieve towers themselves. We see, for example, the molecular sieve towers, when running recycled material, should typically be changed out every 3 to 5 years, which can be quite expensive. And we also see that the water heat exchanger needs to be cleaned quite regularly, every week or 2 weeks. And as well, the process filters are items that do need to be maintained, typically every week to 2 weeks. When we look at the vacuum-based technology, during the development of the product, we understood that maintenance was a key item for customers, and we did our best to reduce as many maintenance items as possible. You'll notice right away that the vacuum drying system, it does not use any desiccant-based material at all, no molecular sieve towers. And the reason for that is the vacuum is the means of reducing moisture content. There's no need for desiccant-based material. This means that one of the key maintenance items is removed, those desiccant towers. As well, this drying system does not require any chilled or tower water to the system. So there's no water heat exchangers that require maintenance. And since this is a system that does not use desiccant material, there is no regeneration process. So there's no need for any regeneration filters. The one area that we could not avoid is that process filters still needed to be part of the system. We recognize customers are using more and more recycled material that has dust, and we need to have filters in place in order to ensure the system is running smoothly. One area where there is a unique item that's added to the vacuum drying system is the introduction of ball valves for the vacuum stage. That is an item that we typically recommend to be proactively maintained once a year. In total, we can see maintenance costs reduced by up to 50% with this new technology. While maintenance is typical for desiccant dryers, processing of rPET material can have a significant impact on the frequency and time required to complete maintenance. Here's some pictures of some key maintenance items and the impact rPET can have in just 1 week of runtime. On the left-hand side, you can see a typical process filter and what that can look like after 1 week of production run. We also see, for example, the oil condenser tank in the middle of the screen. After 1 week, the amount of oil it can collect and the maintenance required to clean that. And then we also see on the right-hand side, a typical heat exchanger cleaned versus after 1 week of running a challenging rPET material. Processing consistency is a critical topic when it comes to processing of any material, but it is especially important when processing rPET because the material is starting the process with higher variation. Being able to control the moisture level with a consistent process will result in improved performance, reduced defect and scrap, and an overall higher quality product. The vacuum dryer is able to hold a relatively uniform vacuum pressure level as its means for reducing moisture. In comparison, desiccant-based technology can see small fluctuations in air dew point level as desiccant towers become saturated and when desiccant towers switch from a saturated tower to a dry tower. On the left-hand side of the screen, you can see a process screen of a desiccant drying system showing the cylinder and cone temperatures, as well as the process air dew point when switching desiccant towers. What I'd like to show you is that when we look at the temperatures, the cylinder temperature and the cone temperature, we see a very stable process. And as well, when we look at the process air dew point, it is certainly a stable process at an acceptable level, but we do see those small fluctuations when changing the desiccant towers. On the right-hand side of the screen, you can see the process screen of a vacuum drying system. Well, we see a stable heating profile across the 3 heating hoppers. The key point from this screen is the consistency in the vacuum level at minus 850 millibar, shown at the bottom of the chart. This vacuum level is the key variable that leads to consistent humidity removal and processing consistency. Earlier in the presentation, I spoke about the challenges that come with processing rPET material. Now I would like to walk you through these challenges and how the vacuum technology can be used to address these challenges. One of the key benefits of the vacuum dryer is that resin is kept at a low temperature, below 160 degrees, for 75% of the drying process. This gentle drying process significantly reduces thermal stress on the resin and limits the potential for thermal degradation. In addition, condensable contaminants are removed when material is subjected to minus 850 millibar vacuum. Instead of these contaminants getting into the process air of the dryer, they are evaporated out along with the water. There is no additional maintenance required due to condensable contaminant generation. The vacuum drying system is equipped with 4 process filters, 1 for each hopper, resulting in 4 times the filtration capacity of a traditional desiccant dryer to handle that higher level of dust that we can see when processing rPET material. Due to the gentle drying process, the vacuum dryer is excellent at avoiding acetaldehyde generation. This is mostly due to the limiting of thermal degradation, and some rPETs can come with higher levels of AA. It is also worth noting that the closed loop integration with the Husky injection molding machine can help to reduce AA levels by recognizing key processing variables like screw torque and injection pressure. Due to the consistent and stable process to remove resin humidity, the vacuum drying system is better suited for managing IV drop. As mentioned earlier, IV drop is a critical variable that can have a big impact on the mechanical strength of the final product and can lead to issues during the stretch blowing process. Since the vacuum dryer processes the material at lower temperature for the first 3 hoppers, it is less sensitive to material that has a lower crystallinity level. And the last significant benefit that we see with the vacuum drying technology is the ability to complete fast resin changeovers in around 2 hours compared to 8 hours for a desiccant drying system. This benefit can result in an additional 6 hours of uptime, which can have a significant impact on the overall equipment effectiveness of your injection molding system. This is a very valuable piece of technology when it comes to companies that are changing materials and recipes often, giving them a higher level of operational flexibility. This is also very valuable even for converters that are running virgin applications that are changing resins quite often. If we look on the screen here, I'll walk you through from the left side to the right side to better illustrate what's happening to create this fast resin changeover. Starting from the left-hand side, we can see that we are processing a material, this gold type of material. As we want to switch materials, we don't end up removing all the material from the vacuum dryer. We can keep running that production into the injection molding machine. And because we have 4 distinct phases, we're able to start loading the new material, which is this blue material, resin B, before we are done production of our first resin A material. What we do is we leave a 1-stage gap, which you can see, to separate the 2 materials. And so that results in around 2 hours of resin changeover time, just being that gap between the 2 different types of resin. You can see here that the vacuum dryer changeover time has been aligned to our fastest mold changeover time, with the goal of giving customers the flexibility they need to run multiple applications or recipes. It is difficult to calculate the value this can bring to each customer, but you can think to yourself how often you're changing resins and what an additional 6 hours of uptime would mean to you and your operation. Now that you've seen the benefits that a vacuum dryer can bring to rPET processing, a question you might have is, how can I install one in my facility? Well, a desiccant drying system cannot be retrofitted into a vacuum dryer, it is important to note that the modular design of vacuum dryers make them very flexible to fit into tight factory constraints. If an older dryer that is having difficulties to process rPET must be replaced, it's very likely that a vacuum dryer can be configured in a way to fit within your work cell. As you can see on the screen here, I've shown 4 potential layout examples of how this system can be fit within your facility. Throughout the presentation, you've seen the left-hand side layout 1, where it's a 2x2 matrix of the phases, but there are a variety of different ways that this type of equipment can be configured. You can think of them almost as building blocks or Lego blocks, where each phase can be put into any position, as shown on the screen. Now, let's recap the key benefits of the vacuum drying technology. First, energy efficiency. This system significantly reduces energy consumption when processing rPET material by eliminating the need of an oil condenser. Next is the low maintenance requirements. Compared to traditional desiccant dryers, the vacuum dryer requires much less upkeep, bringing maintenance costs down by up to 50%. Then we have processing consistency. Thanks to vacuum technology, the drying process remains stable and reliable without being affected by desiccant tower changes. Additionally, we have enhanced rPET processing capability. Moisture and contaminants are effectively removed at much lower temperatures, allowing for gentle drying. Plus, the resin temperature is optimized right before it reaches the injection molding machine inlet. And finally, we have fast resin changeovers. Due to the design of 4 distinct phases, a resin change can be completed in around 2 hours, compared to the 8 hours typically needed with desiccant drying systems. This has a significant impact on the overall equipment effectiveness of the system. All of these benefits work together to improve efficiency, consistency, and cost effectiveness when it comes to rPET processing. That wraps up the main content of our webinar today. If you are interested in downloading our vacuum dryer guide or reaching out about a specific opportunity, simply scan the QR code displayed on your screen here. It will direct you to our vacuum dryer landing page, where you'll find all the resources that you need. Now I'll hand it over to Elizabeth, who will conduct a quick poll and then guide us through the Q&A portion of the webinar. Thank you.
Yes, thank you very much, John, for a really interesting presentation. And yes, like you mentioned, we have a quick poll for you now. Let me just launch that really quick. And yeah, so the question we've got asking here is, which benefit was most valuable to you? And we have the options are energy efficiency, lower maintenance requirements, processing consistency, enhanced rPET processing capability, and fast resin changeovers. So while we wait for audience to vote in this poll, why were you particularly interested in asking this question, John?
So we have found when this system was first introduced back in 2020, and we were looking at what this product, where the value proposition was to our customers, we had certain ideas of things that we felt were important to customers. An example that we were looking at was really trying to reduce energy consumption by removing the need for an oil condenser, and we were really focused on removing maintenance costs as well. And one topic that we weren't really thinking was going to be very valuable for customers was the resin changeover time. And we've noticed since we've started selling the system more and more, that's one of the key value propositions that we're seeing in customers. So even though this system was designed with to meet certain needs, we were slowly learning that there were some other needs that were being more important to customers than we were expecting. So it's always good to ask our customers to see what's important to them.
Yes, and I can see the results are very interestingly. We have 100% going for enhanced rPET processing capability. We very rarely have such strong agreement. Is this in line with what you were expecting, or are you surprised by this result?
I was expecting that I would see more of a mix. I was expecting that most customers would have a variety of different opinions depending on how they're processing their material. I was expecting, with this being mostly a European audience, that energy efficiency would be something quite high. But this is very interesting to see about enhanced rPET processing capability. Of course, that's very, very important. So I guess to answer your question as well, I'm not too surprised that I'm seeing that as one of the leading cases.
Okay, great, thank you. So so before we head into our audience Q&A, just a quick reminder that our survey is now live. And yeah, please make sure that just before you leave the webinar, you fill that in to give us a bit of feedback. Reminder, you can find this survey in the left-hand navigation under Forms, and there should also now be a notification on your screen. So yeah, you should be able to fill that in. Okay, great. So yeah, without further ado, let's head into the Q&A section of this webinar today. Yeah, I wanted to start by asking you, somebody asked us, how many of these vacuum dryers have been sold?
So that's a good question. So since the product was introduced back in 2020, we worked with a few early adopters selling just a few systems back in 2020. And we've slowly seen a ramp up. In the past 2 years, we've seen a much healthier adoption rate on this technology. In total, there's about 50 of these drying systems that have been installed or in the process of being manufactured and sent to customers. So around 50 out there in the marketplace.
Okay, great, thank you. Yeah, somebody else asked us, is the vacuum dryer integrated into the injection molding machine?
So if you are buying a new vacuum drying system as part of a Husky injection molding system, it would certainly come fully integrated to the injection molding machine. This is an exclusive Husky technology. So whenever we sell the technology, it will always come fully integrated to the Husky injection molding machine. We do recognize that there are a lot of opportunities for dryer replacement out in the field. And in those cases, if they are newer injection molding machines, like over the past 6 or 7 years, it is very likely they can be fully integrated to the injection molding machine. But some of the older machines out there in the field, they may have to be standalone drying systems without integration.
Thank you. Somebody else is asking us, just quickly, sorry, to scroll around here a bit. Somebody's asking, as per your explanation, we were expecting to have a reduction in heating temperature during phase 3 because of the vacuum pressure created. Please explain this further.
So sorry, I think the question is, you would expect.
So they were expecting a reduction in heating temperature during phase 3 because of the vacuum pressure created. Yeah, and they just want to ask you to explain this further.
Okay. Yeah, so during phase 3, when we do reduce the pressure, there isn't necessarily a change in temperature because of that, but we do see a slight change in temperature due to the evaporation of water from the material. So when that water is evaporated out of the material, I did have it on my chart. We do see a slight decrease in temperature of the material, which then needs to be addressed in stage 4. So that, yes, there is a slight reduction in temperature as you're expecting.
That makes sense, thank you. Somebody else is asking us, is the system able to process flakes?
So in specialized cases, yes, the system is able to process flakes. There's a lot that goes into understanding how we would look at processing flakes. But just to give you an example, we have been looking at cases where we've introduced a crystallizer as part of this type of solution. So if you're talking about amorphous flakes, that's something where we do have a specialized solution that can be put together for processing of flakes. But predominantly, this is a technology designed mostly for rPET pellets.
Perfect, thank you. Let me see. Oh yes, we have somebody else asking us, can you be more specific with the contaminants? What do you mean by contaminants? Do you mean adhesives, inks, etc.? And at what percentage rate are these contaminants accepted?
Okay. So when I'm referring to condensable contaminants, I'm referring to, for example, oils or glues that are something that's more present in an rPET material. So if I just go back to, say, a desiccant-based drying system and what we see, when processing rPET material, we can see above 160 degrees Celsius that we get condensable contaminants that are generated, and they're going back into the drying system, or they're being collected with an oil condenser. Typically, mostly it's a type of oil or a little bit of glue, and we can see the same thing with a vacuum drying system. So we're removing a type of oil, mostly an oil, but potentially some sort of glue as well that's removed during that vacuum stage. We do see a little bit less condensable contaminant generation because we are keeping the material at a lower temperature, below 160 degrees, but we still see some that's generated and removed during that stage.
Great, thank you. Somebody else is asking us, does the vacuum dryer only work for rPET or other materials also?
That's a very good question. So the design of the material was for the design of the equipment was for the evolving needs of our customers running more rPET material. And that was the main function for its design. But we are seeing a lot of cases where the vacuum drying system is ideal for virgin materials as well. One example I can give you is customers that want reduction in maintenance costs, as well as customers that want the flexibility of faster resin changeovers. So those are typically converters that may be running 100% virgin material, but they want more uptime for their system. And there's a very, very good business case of having those fast resin changeovers. So we're seeing it across the board as a type of technology that is available for virgin or rPET materials. It's a good question.
Thank you. We have not so much a comment question, but a comment. Just run it past you. So somebody's asked or saying, when processing rPET, I don't need an oil condenser and I don't see any preform quality issues. That was just a comment somebody made.
No problem. I'll comment on that quickly. So yeah, we do see that, for example, customers running rPET material on a desiccant-based drying system, and they don't need an oil condenser. They're running effectively. And that comes down to the quantity and quality of the rPET material that they're getting from their source. There are cases where customers have very, very high quality rPET that is almost at a virgin level that can be produced without the need of an oil condenser. Or some customers are running without an oil condenser, but they may see contaminants that are going into the drying system, and maybe they feel they don't need an oil condenser, but they're seeing more maintenance required on the dryer, and there could be a trade-off there. So there are a variety of different ways that they could be running. They could be very good material that they're running that they don't see these kind of issues. It's very dependent on quantity and quality of rPET.
Okay, we have somebody comment, I'm from India and I've never seen your vacuum technology in India, but they said they've been working with Huskies for 10 years. So any plans of making this available in India?
It's available globally. So we'd be happy to look at the opportunity of selling a system in India. We'd be happy to look at the the operation and business case and make sure that this is the right type of technology for your operation. So yes, to answer your question, it is certainly available in India, and we can look through the business case.
Perfect. We had a couple of questions sort of relating to the same thing. Somebody's asking, with the vacuum dryer being a new technology, have customers seen any issues? And then somebody else is also asking about what the maintenance challenges are in general. I guess these two are sort of quite similar, so I thought I'd ask them in one.
Okay. I'll start with the first part. So have we seen challenges in this type of equipment?
With the vacuum dryer being new technology, have customers seen any issues?
Okay. Yep. So this technology was introduced back in 2020, working with some early adopters on introducing the technology. And to be fully honest, yes, at the start there were a few issues that we had seen with early adopters as any new technology would be introduced. I'll even give you the example that I find most common here is we found that when water and contaminants were being removed and brought into the liquid ring vacuum pump, we had it as a maintenance task to flush out that system to remove the potentially dirty water and contaminants in order for that liquid ring vacuum pump to operate effectively. That was something that we put that in the customer's hands to be continuously maintaining this at a rate that wasn't as familiar with them. And we found that that liquid ring vacuum pump was getting more contaminated than what we were hoping to have. So what we did was we made that into an automatic system. So we now have the customer supplying just a tap water to the liquid ring vacuum pump, and it's an automatic maintenance activity. So that was something we saw as a challenge or something that was not working well at the start. And so that's just an example of how the product has evolved since its inception back in 2020.
Great, thank you. And yes, the other questions we had was a bit more broadly about what are the maintenance challenges?
Great. So with respect to maintenance, I'll just explain. I want to kind of compare a little bit to the desiccant-based dryers. So with this being a newer technology and not using desiccant-based technology, we don't have the maintenance on the desiccant material, the desiccant towers, and we don't have any chilled or tower water to the system. So there's no maintenance of any heat exchangers. But what we are seeing is we do have 4 process filters that do require maintenance. And it can be every week to 2 weeks. And that's just because it is collecting dust from each of the 4 phases. I had mentioned as well that something unique to the vacuum dryer is the 4 ball valves to create the vacuum chamber. Keeping a steady vacuum level is very important to the process. So we do suggest that there's proactive maintenance once a year on replacing those ball valves just to ensure a stable vacuum level. That is certainly a unique maintenance item. Other than that, we see very little maintenance on the system. It's all generally basic technologies with blowers and fans and heaters. So very little maintenance.
That's always good to hear. So I think we've got time for a couple more questions. Click that one on already. Somebody asking, can I retrofit one of my existing desiccant dryers into the vacuum dryer?
So because the technology is quite different, you can see a desiccant dryer is usually one large mono hopper, and the vacuum dryer is 4 distinct hoppers. We aren't able to retrofit a desiccant-based dryer into a vacuum dryer. However, the vacuum dryer is a product that can typically fit within the same space constraint of a desiccant dryer that's out there in the field. So while we can't retrofit it, it's very likely that it can be replaced within those factory constraints.
Great. Perfect, thank you. So, somebody else is asking us, have there been any vacuum dryers installed in Europe?
Yes, so quite a few. So we do work with our key supplier, PT Solutions, on this technology, and they're located in Europe, and that's where some of the early adopters were existing back in 2020, and since then that's been a very common place where this type of equipment has been sold, typically throughout Europe. So yes, it's probably most common in the European market.
Perfect, thank you. And yeah, I think we've got time for one more question, which is, does the vacuum dryer require chilled to tower water?
So no, so that is one of the unique cases for this technology. There is no chilled water or tower required for the drying system itself. So we do need tap water provided to flushing of the liquid ring vacuum pump, but there's no chilled water or tower water required for the drying system itself.
Perfect, thank you. And that was quite a concise answer, so I'll ask one more question. If someone's asking if we mix rPET and vPET resin in a certain proportion, then how can this system help with drying?
So yes, we see that a lot with customers that are running mixes of call it 20% rPET with 80% virgin, or 50-50, or any mixture that's possible. Yeah, we see that quite often, and the processing through the system is very consistent regardless of the type of material. So as long as that bulk density is generally quite similar, it stays in the right mixture ratio, then it can be both materials can be processed through the drying system. In general, the drying system keeping the material at a lower temperature, both materials would benefit from that gentle form of drying, and they would both achieve the right temperature levels and humidity levels when reaching the injection molding machine. So definitely we see customers running mixes, and this dryer is fully equipped to support that.
Perfect, thank you. Okay, so I think that's all we've got time for today, but don't worry if we didn't get the chance to answer your question today. I'm sure the Husky team will be very happy to get back to you anyway and answer your question later. Or feel free to obviously reach out to John. You'll see his contact details there on the screen, and yeah, ask him about anything you've seen today, any questions, or yeah, anything in that vein. So yeah, he'll be very happy to get back to you. Yeah, the webinar will be available on demand within the next couple of days, and you'll be sent a link to access it in case you want to recap on anything you've seen today. And yeah, I'd like to remind you again before leaving today, please make sure to fill in our survey to share our thoughts on this webinar and yeah, help us to make them even better. So yeah, that just leaves me to say thank you to the speaker today, John Murphy, for sharing his insights and for answering all of the questions. Yeah, thank you very much, and goodbye. Have a nice afternoon.
And thank you very much, Elizabeth. Really appreciate you having me on today. And thank you to everyone that came to hear me today. I hope you were able to learn a few things. So thank you very much.